Welcome to today's project recap. My name is David Kersley, and this is
Tyler Reed.
All right. So earlier this year, we did a project, Tyler, where we collaborated on. We did a live event in Chicago. We did brought together like 3 or 4 pieces of technology. We did a live event. We thought we'd do a little project recap and bring everybody up to speed on what we'd worked on. So
yeah, Top Golf, Chicago summertime. That was an awesome event.
Yeah, we had a lot of people there. It's a good event. So thought what we do is kind of talk about the initial concept and then just work through all the phases that went into it, right? We had this idea. My background is I spent the last 20 years in the golf industry, designing everything from putters to drivers to training aids, kind of everything across the board. And it's still one of my great passions and something I still do, right? So one of the things I wanted to do was bring this in and start talking about the new technology and how we can improve product design, right? So with product design, there's always a lot of theories, right? Like, oh, this works or this doesn't work, but can I prove it? And so that led us to some CAD models, and that's where kind of we brought you in with the new technologies on the printing side. Like, what can we really do? Just because I can make it on screen doesn't mean it's manufacturable.
Yeah, I learned that. That's very true about you.
Yep. And we kind of learned that on this project, actually, right?
Yeah.
With some of the 3D printings. Like I had some design cues or features built in there. And then you were like, hey, we can't do that. We have to move a different direction. And it kind of came out as a great project. I think the final product is awesome. So, and I know it's still evolving a little bit, but we're getting there.
Yeah, it's an ongoing project. We have a great base asset in your design, which you have 20 years experience of knowing like the technical aspects of designing golf equipment. I have 10 years experience just printing knickknacks and toys, so we make a good team, I think, together. But it's very much an ongoing project. I think the goal is to build more of these putters and give them out in future events. I can't stress enough like how fun that in-person event was. But when we were talking and presenting in person, it's very much like, here's the software, here's the hardware, here's what we did, but less of the why. And so that's what I'm hoping to get out of this session is just a discussion between you and I is like, why did we do things? What were we trying to avoid? What did we step into without realizing it? And how did we get past that?
Yeah, absolutely. It was a fun project. I know it, like you said, it's still ongoing, and we got all these cool little gadgets here on the table, but let's just jump right in kind of the initial design phase I think we were looking at. Okay. So again, part of it is I want to use the software to move past design theories, right? We've had a lot of design theories in golf. A lot of stuff is just kind of tried and true. We know it's worked, but what can I do with SolidWorks? What can I do with my software to kind of prove or disprove that theory?
Okay,
right?
So you're looking for a validation.
Yeah, absolutely. And we were able to kind of do that with quite a few things. So as far as the initial design phase, and we're going to call some things up on the screen here, there are some rules and regulations to golf. It has to be a certain footprint size, right? Okay. The putter has to be wider as far as heel to toe. The putter has to be wider this way than it is in the depth, front to back.
Okay. So you have like the rules of the sport that the players have to follow, and then you have rules of the equipment that the designers have to follow.
Absolutely.
Of course.
Which is kind of cool. There are rules and regulations to just about everything. So, how could we take this and also prove some other design theories that we're going to run into here in just a little bit? Okay. So we got rules of golf. These are kind of some of the images you see here. These are the model types that are currently on the market. Okay. All different model types. And they're looking at these different model types, and the theory is, hey, I'm looking at something that has a greater moment of inertia. And so in golf, when we talk about moment of inertia, kind of think of it as like a barbell, right? If I hold the barbell, it's really long, and I put on my weight and I hold it right here, right? And I say, Tyler, go out and push over here. This is kind of like the face at impact. So if I go over and I push over here, it's going to twist pretty easy, right?
Yep.
But if I take
you have leverage.
Yeah. So now if I put my arms and put the weight out here kind of in a brace and you push on that face, it stays more stable.
Okay.
Right? So now I'm moving the weight to the perimeter, stabilize that hit, right?
Because you're trying to reduce rotation.
I'm trying to reduce rotation so that the ball stays truer on its roll to its path.
That makes sense.
Right? So one of the things that we try and do is stabilize that head. Because unfortunately, unless you're a tiger, you're not hitting it in the center of the face every single time,
Sure.
right? It could be as much as a ½ inch off center. And a ½ inch off center makes a huge difference. So, this is where we were going with it. Can we prove or disprove that?
So you have to design for like worst case scenario. You have to design for you have different customers based on the skill level of who you're designing for, right? Yeah, that's pretty cool.
Yeah, when we kind of get a little bit more into that here in just a little bit. We'll talk about kind of the design criteria.
Okay.
You can almost look at it as like, how marketing will do a storyboard. Like this person fits into this golf category and they wear this watch and they drive these cars.
Yeah.
We kind of do that with golf equipment. Like, what's the handicap? What's the skill set? And who are we trying to help?
Okay. And when I look at these designs, these are almost all machine designs. And most equipment is either machined or forged or cast right now.
Yes.
But we do see some manufacturers providing tour players with 3D printed parts, right?
That is correct. Yeah. So in the past 2 to 3 years, you've seen 3D printed parts. And some of them will say that they're fully 3D printed and there may be only one component.
Yeah.
What we decided to do on this one, when you and I were talking, was like, what if we 3D printed the whole thing?
Yeah.
And that's kind of a differentiator.
It's cool. You know, on the topic of 3D printing for the tour players, like you could print different styles of putters or wedges or irons per player, per event, per condition. And I think that customization is like the holy grail of golf equipment design, right?
Absolutely. Golfers are funny. They're very brand focused. Some people like brand A versus brand B, and they never really move off of it. But if they find something unique that's different than everybody else, they like to have that in their bag.
It's the potential for an edge.
Yeah, like, oh, look at this. I've got a X number $100 putter versus your smaller value, so I'm going to be better, right? So that does happen quite a bit.
Cool.
So golfers are funny like that. And I say golfers, but I'm one of them. So when we look at kind of these images here, we see that these are the market trends. These are kind of the modern designs. And this was where we kind of started. Like, hey, how do I take the rules of golf? I kind of take these modern shapes, and how do I bring them into kind of what we see here, this block image here. Okay. So we took SolidWorks, created our image, and we just took a block. All I wanted to do was take some design cues. Now what you see there is you kind of see the golf ball in the front, kind of that sketch. And what we're trying to do as designers is, and some folks may not know this who play golf, is we're trying to always bring your eyes forward on the putter. Again, that just allows you to look at the ball. We don't want you really focusing on the putter. If there's all this kind of crazy design criteria and shaping going on
like
here in
this?
the back, like that, like I would totally be looking at the back.
This is not your design.
No.
Yeah, okay.
But I would be looking at the back.
Yeah.
Right, and I wouldn't be focused on trying to hit the ball.
Yeah, okay.
So I might be focused on the putter design itself, and I'm looking back here. And when I'm looking back here, the putter could be going any number of directions.
If the putter looks too good, it could be a distraction.
It could be.
When I look at this, I see an F22. Like it has the lines of an F22.
Yeah, that's a good way to look at it. Very aerodynamic, but again, notice that we're trying to use the shape to kind of draw to the front of the ball. Yeah, because we want the putter to hit, or the golfer to hit right through the ball.
Like a visual cue.
Yeah.
That's cool.
And most people don't even know that's there, but as club designers, we've been doing it for years.
Yeah.
Like, hey, did you even know that? And most people don't, and now they do, right? Kind of let that secret out.
Subliminal design.
Yeah. So then, we kind of wanted to figure out a way, because you're in one location here in Utah. I'm in Austin, Texas. We had a team in Chicago, and we had multiple locations, and the question was, how do we bring everybody together, right? So what we did is we actually used the 3D Experience platform. It's an online PLM tool that allowed us to collaborate together. We were able to look at our designs. We were to kind of share back and forth. You and I were able to look in some of these videos here. You can see, hey, guess what? This is working. This isn't working. Hey, here's our timeline. I had revision control. Yeah. Everything was in place, and it allowed us to really control this project, which was really cool. And, we had the swim community here where you were like, hey, Dave, I like the initial design, but it's not working. So we got to make some changes.
Right. That was important for me to be able to communicate to you as early on in the design process that the direction that you're heading is going to cause me more grief. Yeah. So then there could be a discussion about the value of it and if you could take a different route, or, I'm going to have to figure out a way to get past it because it's important to the design. Yeah, because like I said earlier, it's one thing, I can design anything on paper or anything on CAD, but is it manufacturable?
that's one thing as engineers we always have to pay attention to, right? And I'm thinking maybe a little like we're kind of got unlimited technology. We can do whatever we want.
Yeah.
But then you quickly learn there are some limitations, right?
Yeah. And a lot of times it's best to have that conversation in person. But I will say just being able to type a comment and kind of remove myself from that face-to-face interaction and maybe some of the anxiety or pressure that carries with it is kind of cool. Like just being able to comment like, hey, double check this because it's going to be an issue.
Yeah.
Made my life easier.
Yeah. And it's nice too because I might be working on the project and you might not be. And you just get a little notification like, hey, I got to go look at this. Dave needs some help on this. Or in your case, you messaged me back and I'm like, oh man, we got some more work to do.
Yeah.
So that was okay. Again, I got full revision control. All our files were here. The team could see it and it worked out really well, I think. So we had that block, right? And we started with just this shape that we kind of see on screen here now is what we did is we just started with a giant mass. And we wanted to use simulation. What in simulation, what in SolidWorks, what technology can we kind of use and disprove? How do we make the design better?
Okay.
Right? As engineers, that's one thing we're always trying to do. Build a better mousetrap. Can I make a better golf putter?
Yeah.
Right? And so the Topology software really allowed us to do a couple things.
Okay.
One, we wanted to figure out where is mass really needed, right? Again, I can design anything, but is it functional? Form, fit, function, right? In this case, I needed to know, I want to be very purpose driven as to what we're doing.
Okay.
Right? So let's put mass only exactly where we need it and let's improve the performance with that. So that's where we kind of took it from there. Okay. And then we said, okay, I got this block and you can see over here on the left side, we implemented several things. We implemented like a center of gravity. We had some protected regions on the bottom of the putter where we said, hey, we know we're going to put mass.
Okay.
And these are kind of some protected regions. We also wanted to protect the face or what we call distributed mass areas. And so we plugged those in. At the same time, we wanted to use topology optimization. And we said, hey, we have some mass constraints. This block, as it is now with a stainless steel material, is around 1,100 grams. Standard putter is around 350 to 400 grams.
Okay.
So we had a lot to get out of there.
Yeah, you got the Mjolnir of putters.
Yeah. So we got to really move weight. But again, where does that weight need to be? So again, that's where we kind of ran the topology. Would it tell us what we needed?
Okay.
The other thing there was sound.
Really?
Yeah, sound is so critical to golfers. Golfers equate sound to feel, right?
Okay.
If it sounds like an old metal tin trash can, even though it might perform great, they're going to not pick it up, right? With golfers and putters, if it's real clicky sounding, they perceive the putter as to be hard. And they're like, oh, I don't like the sound. This is a hard-faced putter, or it just smacks off, right?
Okay.
Then there's the other end of the spectrum, whereas if it's too soft a face insert or something like that, it'll sound mushy, right?
Okay.
I know that's a technical term, right?
Yeah.
But it sounds too soft or muted, and the golfer goes, it's too soft, I don't like it. I'm not getting enough energy into the ball, right?
And you had the tools to take that into account?
Well, actually what we did on this is, so we plugged in a frequency that we wanted the topology to hit. Okay. We said, hey, we want to be around 1,000 hertz on this. And that's, again, that's golfer to golfer. Again, sound is feel. 1,000 might sound great to you. It might sound a little clicky to somebody else. So we actually programmed that in.
Oh, wow.
So when we programmed that in, we let the software kind of run itself. And we started to get up these kind of these final images here. So what you see here is you kind of see the yellow is the topology part. The sketch is kind of what we started with as far as a footprint.
Yeah.
And so now, as an engineer, I go, holy cow, look at all this open area that I don't need mass.
Right.
Right? So now the question is, okay, what do I do with this? And so part of you looks at it and goes, this is really overwhelming. I don't really know what to do with it, right? So then we start to look at it and we start to do things. So this is what it would look like if we did a non-symmetrical design.
Okay.
This one here, I'm going to back up one. This one here is when we put in a symmetrical constraint. Symmetrical, again, what I do to like an algebraic equation. What I do to the left side, I want to do to the right. So we said, hey, use a symmetric constraint and make the mass distributedly even. Of that 350 grams, I want it symmetrical with all the other parameters we plugged in place. And this was kind of the shape that it came out to be.
And I can see mass and frequency are your main design criteria.
Yeah.
Okay. And it just so happens to be that it's creating this horseshoe shape that, puts you in that realm of, the preferred moment of inertia.
Yeah.
And is that just a coincidence, or is there something about the two design constraints?
Yeah, so again, it kind of gets back to, so it's a couple of things there. One, we wanted to make sure that we could prove that theory of bracing it out on the perimeter. And what we see from that, this slide here, is we can see that that's kind of true. Like you can see the weight is kind of out on the perimeter. I'm stabilizing it.
Yeah.
But it's kind of unique in the shape that
that's true.
kind of made, right? So now we're like, man, these two arms kind of going back to the preserved regions where we're going to have mass look kind of interesting. So, it was kind of like, okay, we kind of thought that was true.
Yeah.
Now we know it is true. Right?
And it foreshadows the shape that we ended up with.
Yeah. And so then now we have this shape, right? And this is what it would look like symmetrical. Again, this is what it looked like asymmetrical. Like if I wanted to use the same criteria, but I said, I don't care anything other than, it doesn't have to be symmetrical. You can see that all the mass is now down heelward.
Yeah.
So what it's trying to do is it's trying to protect that putter face. So when I hit it on the heel, the putter's going to do this. And now what it's trying to do is it's trying to stabilize itself.
Okay.
Because the CG of the putter is always trying to rotate around the center axis of the shaft, right? And so now we're putting these two together and it's creating a more stable shape. It's reducing that moment, I guess.
Why not put the shaft in the center of the putter?
You absolutely can. But to be honest with you, when you look at sales, not that many center shafted putters actually sell. So, and that led to something we did a couple years ago with Shivani, is we started studying where the ideal location for the hosel should be.
Oh, that's right. I remember that project.
Yeah, so we actually did that, and we found a location where it actually stabilized the putter face on 10-foot putts. So
cool.
Yeah, so that's where we utilize this location here. So then we start to getting into designing with intent, right? So as a golfer and as when I first got into golf, the guy told me, hey, to be a good designer, you need to be a good fitter. And I never really understand that. I'm going to call up some criteria here, and we're going to touch on a couple of these here. But you can kind of see all of these on board. These are just a few of kind of what we target, right? Length. What is the total length of the putter? And what is the total what is the loft on the putter? Criteria like that. But what the initial phrase of you need to be a good fitter to be a good designer is, just because I designed it a certain way doesn't mean people are going to use it a certain way, right? Like, it's amazing to design something in your head. You're like, I'm so excited.
Yeah.
I know this is going to work. And then you watch somebody and you go, this totally didn't work.
Yeah.
Like, I never intended for somebody to actually use it that way.
And that's a truth for every designer, right? In every industry.
Yeah.
You're always having to anticipate what misuse looks like, in assessing the risk of misuse and designing around misuse. And if you can guide it towards, like, if your design takes into account the misuse and elevates the performance of a misuse, that's a good design.
Yeah, and that's where the topology helped.
Yeah.
And that's where we also ran things like kinematic motion studies. So now I can take the putter in the software and I can say, hey, if I hit it off center X number of every quarter of an inch, heel and toe, where's it the most stable? And as you got this criteria kind of we're looking at on screen, but one of the things I look at is the 10-foot putt, right? The average golfer hits it about 40 to 45 feet from the pin on their approach shots.
Okay.
Tour players are around 30.
Okay.
But, Tyler, let's just say you shoot 102 every time you play, right? That's about average.
Let's pretend. Yeah.
Right? But you want to shoot in the 90s.
Okay.
And you came to me, say, David, I need to be fit for, most people come and say, David, I want to be fit for a driver. And I usually go, let's take a look at your putter first, because you're going to have 8 to 10 putts in that 10-foot window per round. You miss all of them, you shot 102. If I get you into the right putter and I have got a putter that's designed properly, maybe you make 5 of those and you make 97. So now you're breaking 100. And that was always your goal. Or even maybe you're trying to go from 82 to 77, right? So suddenly if I make 5 or 6 or 7 of these around, my scores are getting better and better. And if you do something, you're successful with it, it breeds confidence. And if you can putt well, you start to play other parts of your golf game well, right?
Yeah.
So I've always focused as a designer, like, what is it doing at 10 feet?
Okay.
Golfers, they do some crazy things. So, I always want to focus in at that 10-foot mark. So again, look, sound, loft, lie, all that gets factored in, right? So when we look at it, I've got all this, I've got the design. I thought I was ready, and I was like, hey, Tyler, let's take a look at this initial design. And I, shared it with you on the platform. Now you've got it. And it's kind of like, what can we do, right? And I guess we kind of learned a bunch of stuff, right? Like, hey, Dave, that was kind of a good idea, but it's not going to work.
Yeah.
Especially on the metal printing side, right?
Yeah. And I learned a lot just sitting here. Even though we had already done most of this project and we already presented it, just hearing you explain it face to face was actually really helpful to me. And I probably should have taken the time to ask more questions early
That's
on,
all right, go for it.
before we pass it on. That outline of the design methodology was pretty enlightening. I didn't know a lot about that.
Yeah.
But it was eventually passed to me, and my job was to take those designs and bring them into the physical world with the help of mostly 3D printing. We do a little bit of machining here so that we could get something in our hands to test, right? And if it was good to go the first time around, we would have given that away, but we didn't end up giving that one away for reasons, we'll say that. So when it came to the 3D printing component of this, I have a lot of tools here in the lab here, and I take advantage of all of those. We have thermoplastic printers, we have thermoset printers, we have metal printers, and they each have their own advantages and disadvantages. So in a project like this, it makes a lot of sense to incorporate different technologies. Just because I'm taking advantage of all of those technologies doesn't mean that someone would need one of everything. You can get by with a basic FDM thermoplastic printer can get you a long way. It's not going to be printing end-use metal parts, but it can get you further down the road. So we have some polyjet machines here in the office. Polyjet machines are thermoset resin printers. They work a lot like an inkjet printer at home. And in fact, you can load up color resins and do full color prints. So that's one thing I wanted to experiment with, was make these distracting. I didn't know that was going to take away from the usability of the putter, so I'm sorry for that. But on the polyjet printer, it's as simple as taking a image file, like a JPEG file or a PNG file, in SOLIDWORKS, laying it down in SOLIDWORKS as an appearance. So we use custom appearances for this, and we can create cool designs like this. I think this is pretty cool.
That's pretty awesome.
At the time we did this, the James Webb Space Telescope had just launched, so I did a few putters with the images, the first images from JWST, and we did all sorts of things. One thing I didn't do was a big arrow that's like, here's the ball, although I could have probably benefited from that. The nice thing about PolyJet is the print times are fairly quick, relatively speaking, and we could fit dozens of these on a build and print those overnight. And just test a lot of designs all at the same time. So when we're talking about design testing, it was really important for us to get parts in our hands so that we could start assembling them. One thing that's really hard to anticipate when we're designing is anticipating how parts are going to go together, and then if they need to be disassembled, how are they going to go apart? And can you do that over and over and over? Me as a designer, I'm not good at that. So I usually fall back on creating prototypes, trying to fit them together and see where they fit. Taking a Dremel tool and massaging the shape a little bit to get it to work, and that's what we did here. But I came at you with a few design changes. So we took these registering bosses, these 4 bosses, and we tapered them. That helped them kind of slide into place together. We changed that whole front end. We shaved off that front end, maybe like 20 thousandths, I think. We took that off so it fit a little bit nicer. I added a 3D stripe to it, which I took some design liberty. I don't know if that affected anything on your end. And then I created some registration features so that we could print the decals separately and just slide that into place.
Yeah, that was a great idea.
Thanks. Oh, actually, here is the image of the JWST image. We've got a nice 90s pop one. I had some fun with these.
Yeah.
We printed these on the J850 here in Salt Lake City, and also the J55.
Okay.
The J55 is a pretty unusual machine if you haven't seen it in person. The print volume is a donut shape. So the platen spins at a constant RPM, and then the print head moves down along the radius, and it has fewer moving components overall while it's printing, so the part quality is just nuts.
Yeah.
That was it for the PolyJet. PolyJet is more of a fit and form and visual prototyping tool. It can be used for tools and some of these other things, but it's not its best fit. Okay. So I was mostly focused on printing it in PolyJet rapidly so that we could assemble it, figure out what design changes need to be made, and then doing those and then before we go over to the metal printing.
Yeah.
We do have some design changes that were needed for the metal printing.
Yeah.
So you fed me a model that looks like what you see here on the screen. It had a lot of ribbing, like truss structure. And one question I had for you is, what role does that truss structure play in your design? Because I felt like it was something I was going to want to change.
Yeah.
When it comes to printing in general, there are, there's a need to create support structures. Like typically when we're printing, if something's straight up, great. And then as you start to tilt down, like towards the horizontal, once it gets below a certain level, it can't self-support itself. So we have to fill up that negative space with a sacrificial material, support material. You saw it in the images from the PolyJet. These things were totally coated in a separate material. That's the support material. And a lot of us are used to seeing this with FDM. And with our Stratasys machines, that support material is water soluble. So we can basically design whatever we want because the support removal process is pretty simple. We just dump it in a bath, walk away, come back a couple hours later, and support's gone. But with metal, it's not so easy. With metal, the support structures are made of the same material, same alloy as whatever metal we're printing in. And so removing that is not as simple as just dissolving it away. You have to get in there mechanically and remove it, either with pliers or machine tools or anything in between there. So if you can design around needing supports, that's ideal. And with these 0-degree overhangs that were in the truss structure, like pretty much we had to eliminate those. So I went into Magix. Magix is the tool that we use to slice these models and do all the support structure generation. There's a module in there called structures, and we can do lattice substitution there. So basically, I separated out some solid bodies in SOLIDWORKS, and I said, turn these solid bodies into lattice structures by basically narrowing it down to a voxel, like a 3-dimensional pixel. And when we print or when we design anything solid, that it's a box, it's a cube. But we can start to substitute that 100% dense cube with lattices that are maybe 40% dense, 50% dense, 60% dense, and then build those up together. That's called lattice substitution, and that's what I did. And we don't think it hurt the performance, right?
No, absolutely not. And so the reason you asked a good question earlier about why did I put those trusses in there. One thing you don't want is big open cavities. Those open cavities, so you saw those structures in there. One, structural support was kind of part of it. The other part was I didn't want a sound chamber where, again, sound or something resonating got in these pockets and started to make a funky sound.
Oh, yeah.
So the best way to do it was like, hey, can I structurally support it, make that metal component stronger? And 2, can I eliminate any chance of a weird sound pocket being in it?
Okay, that makes sense. You could have some fun with that.
Yeah.
Too. So we eventually decided on printing these upright and 3 at a time, which is what you see here. And this is actually the first print that we did with these parts. It looked like on our current gen machine, this was a 54-hour print. We have a 2nd gen machine due here in Salt Lake very soon. And I ran the numbers, and this would be just a shy of 10-hour print on that 2nd gen machine.
Wow.
So a 2nd gen machine from Xact Metal, much quicker. That's the main differentiator. Build size and other things are pretty much the same. Okay. Much quicker. And I was, honestly, to be able to create stainless steel parts of this level of complexity and basically just hit a button and walk away for, in this case, a couple days and come back, and this is the quality of parts that I had, I was blown away.
Yeah. And how many different materials can you print on that printer currently?
That's a good question. So we can print a half dozen to a dozen different materials right now. With that particular printer, you can bring your own powders if you're willing to do the parameter development. So if you have the background to like set up a DOE and figure out what does my laser power have to be, my scan rate, scan hatch distance, all that things, you can, any material that's weldable to itself, autogenously weldable is the term here, can be printed in this style printer. It's a powder bed fusion printer. You lay down a very thin layer of metal alloy, and then that gets traced with a laser. In this case, we're using a 200 watt laser, fiber laser, and it micro welds the path, and it will do a full level, and then it will go down. In this case, it goes down 30 microns, and it does the process again. And so we build it up from the build plate up. We always start with a fresh build plate, or I'll say fresh. Like this one's been well used, but this one's ready to go.
Okay, so I can reuse this tray or build plate over and over.
Yeah.
Do you just break these off with a saw or like a chisel of some sort and then go over and polish this so you can reuse it again and again and again? Because this looks like it'd be expensive over.
We do a little bit of both.
Okay.
So if I have a build like this, let's say, these are built really solidly to the build plate. We have 316L stainless here, and we have A2 tool steel here in the build plate. These get cut off with a bandsaw, and that leaves some evidence of support structure. When I print these, I lift them up about 3 millimeters, and that gives me enough space for the kerf of the blade. So in order to reuse it, I have to get rid of that remaining support. I'll either use an angle grinder and a flap disc and just sand it off, or I'll chuck it up in the milling machine and I'll mill it off. If it's a large cross section and it's going to take me a little while with the flap disc, I'll just machine it off. But when I machine it, I have to take 10 or 15 thousandths off the whole plate. Whereas if I just use the flap disc, I don't really lose any of the plate. So I try to use the flap disc whenever possible, and we beat these things down pretty bad, but this is ready to use. It's very tolerant. The machine is tolerant of any imperfections in this plate. You can see bandsaw marks, some fresh sanding marks. This one's not been machined, where a machine surface would look like this at the bottom side. So we do a combo of both. The next part that we printed was the face, and with the face we can see a different support structure. This one was made to be removed by hand. Orienting this part was a little bit tricky. We had to have a discussion around what surfaces needed to be dimensionally accurate and hopefully remove support from those or eliminate even placing support in those. Or alternatively, only put support there, knowing that we'll machine the support off and we'll get our dimensionally accurate tolerances. So that's what we did in this case, is we oriented it so that support was only touching places where we knew we were going to machine away.
Did you have to scale it up by chance? Like, I'm going to scale it up knowing that I'm, like, let's say I gave you the model. Did you have to scale it up to get this shape, or how accurate did they come out to the original models? Yeah,
so in theory, you wouldn't have to change the scaling factor. That's done by the software itself. It gives you access to change scaling, so if you needed to, you could do it. And in some technologies, even one of our own, like that's something that you maybe are kind of in. But for this specific technology and this specific implementation of it, I didn't have to touch the scaling.
Oh, nice.
Yep. So powder bed fusion is generally accurate to 0.2%. So that's 0.002 inch per inch. So on a part that's of this size, it's about 3 inches. You're at about plus or minus 6 thousandths is the expected tolerance.
Cool.
So on this part, we have support structure that is designed to be broken away. And I've got some tools to show you how it's done. So I can use snips or pliers and just break it away. Let's see.
Yeah, that's easy.
Not too bad.
Time consuming, but not too bad.
Yeah, I mean, it's not too bad. And if I broke my snips.
That's awesome.
Okay, well, we'll use pliers instead. I wonder if those snips had fatigued from doing this a few times. But so you just break it off, and you're left with a relatively rough surface.
That's nice. Yeah.
Yeah. So we have another part here, this one. That's the surface that's left after removing the support by hand and then just hand filing that surface. Okay. And then same with this one, except we also hit this with a belt sander. And then we wire brush the whole part. That's why it's that shiny metal versus this is the as printed
Looks
finish.
good.
Yeah. But this one's been processed with only hand tools.
Okay.
The one that we built originally, we machined away. And we've got some video of that. We're going to show machining that one away. All right, so one of the challenging parts of the design were these screws.
Yeah.
Like they're weights, but they're also screws. Like they're the main mechanism for holding the putter together, right?
Yep. And this is a great case of, hey, this works great in my head and it works great on paper, but is it manufacturable?
With the tools that we have.
With what we have.
Yeah, with the tools that we have. And we could manufacture them, but we had to make some changes, right? So in the image here, you can see that the final part is a machine screw with the Go logo and a hex feature to screw it in. And the printed part, I added material to the boss and to the upper side as well. And the theory being that I need to be able to machine those threads. I can't print those threads of that size. I think those were quarter 20 or quarter 28, something like that. I could print them, but they're just not going to be high quality threads. So my preference was to machine them. Yeah. And then I needed to give myself some material to hold in the chuck. So the good thing is we printed a ton of those, but even in that photo, you can see this is a little rough for features of that size. So once we tackled the face and the weights, the next step was to go beyond PolyJet with this part here. So we knew that we needed something more durable than these acrylic-based resins that we have on the PolyJet side. And that's where we turn to our Origin system. Origin is a DLP style printer. So it does use a thermoset resin just like PolyJet, but the way it cures the resins is vastly different. And we have access to more viscous resins in that platform. And it just so happens that viscous resins tend to have better mechanical properties. So we can achieve a lot of the same surface quality, dimensionality that we can with PolyJet, but we can do it at a more rapid pace and with more appropriate materials for like putting this in a putter in someone's hands going out on the course. So we turned to Origin for that. With Origin, we process these in both NetFab and GrabCAD Print. You do have to build in support structures, and Origin is a great technology for printing high volumes of this too, which was something that we didn't really discuss. We were mostly just focused on making 1, 2, maybe 5 or 6 in total. But if we were going to ramp into like some sort of low volume production, Origin could keep up with that quantity. And laser powder bed fusion could as well. Probably not this specific machine, but there are machines from other partners that we have, like Velo, that could print these parts at a production level.
About the same time? So somewhere between the 10 to 20 hour window to, like we were talking on these three?
Yeah, probably faster. Oh, wow. Probably faster. So production powder bed fusion printers like that tend to have larger build volumes. So your highest efficiency normally is when you fill the build volume. So larger build volume, you're gonna fill it up, and then they add more lasers. So you'll get 2 lasers up to 8 lasers on some of these machines and firing them very quickly, and higher power lasers. So we were on a 200 watt laser, we can only laser so fast. But if we have, say, 1 kilowatt of power, typically we can take advantage of that and laser even faster.
Yeah.
So it would be, I would anticipate your print time per part would go way down versus what we saw there. Yeah, part of that is a lot of the print time is just not, it's not lasing, it's their recoat time.
Okay.
So maybe 50% of the time is the machine just recoating layers. And so if you take that recoat time and know that it's set for the height of the print, but you have now 20 parts versus 3 parts, your efficiency is going to go way up. So on the post-processing side, we talked a little bit about what we needed to do with these parts. This is where we brought in the FDM printer to take advantage of what it's good at, and that is creating robust, cheap parts that are fairly chemical resistant and can withstand the forces and the chemicals that we needed to machine these components. So in the first part, our goal was to machine this surface. So once I cut these off, that was a mating surface, that bottom surface here. So we had to cut those off, and we used the soft jaw that you see up on the screen here to hold that in place for op 1 to just machine that surface. Op 2 was machining this surface here where all of the support material was, and then it also gave us access to this top surface so we could bore out this hole here, which you wanted to a very tight tolerance. Do you remember what it was off the top of your head?
It was a clearance of 2 thou.
2 thou total tolerance, and we hit it.
Yep.
I hit it. So honestly, I don't know how this worked, but it worked. If you see the soft jaw design here, it just squeezes this model between these 2 soft jaws. And if I try to do it, which maybe I will, even if you squeeze this off center just a little bit, it just flies apart.
Yeah.
It just flies apart. But it actually worked. You know, it just happens to be that everything's nice and straight in the machine tool. But as soon as I go to squeeze this, it's gonna fly apart.
Yeah.
Are you ready for it?
Go for it.
I had to do it. I had to do it. But it didn't happen. So we were able to machine that, roll the footage, it worked. And I have to give the designer credit because he trusted it. Great thing about these soft jaw tools is that we can cut right into them if we needed. So panning or sweeping across that middle surface, we could cut right into the soft jaw, no problem. And we can iterate these quickly. So if it didn't work, you know, probably no harm, no foul.
Yeah.
And then op 3 was to cut that top surface, which I thought it would be fun to cut a design in there. We didn't end up doing this for the first putter we printed.
Correct.
But you came at me with a second design that had some features on the back side here. And because of these extra features, I oriented it differently. And now on this one, for sure, once we cut this off, we're gonna have to machine that top surface.
Yeah.
Because I actually added 3 millimeters of material to the top. I just used Move Face in SOLIDWORKS and just pushed it up, and we'll machine that away. And we'll take advantage of that third set of soft jaws, which so far we hadn't used before. So I'm looking forward to that. Designing of these soft jaws goes relatively quickly because you're just designing for intent. We know with FDM printer, we don't have to really take advantage of, or we don't have to avoid putting support material in certain places. We just design it intuitively. It designs quicker that way. And the overall print time for all of those soft jaws looks like was 13 hours on our F370. So that's an overnight print.
Yeah.
The turnaround time, one of the guys on my team designed these in a day. We printed them overnight. So it was a 1-day turnaround for all those soft jaws. Oh, see here you can see the setup.
Yep.
Yeah.
It's nice to have expendable tooling, right?
Sorta. Yeah.
You know?
On the soft jaw side.
Yeah.
On the soft jaw side. But you said that right as the probe came up, and those probes are like notorious for being broken. Yeah, so not so expendable. And then here in Op 4, we were tackling the threading of these little parts here. So we chucked these up in a 3-jaw chuck, and we cut the boss down to size, and then we came in thread milled. Okay. I switched it to 1/4-28 on the thread mill. Okay. We programmed these in SOLIDWORKS CAM within SOLIDWORKS, output it to the Tormach, which we have that post processor on our webpage if anyone wants to use SOLIDWORKS CAM and Tormach milling or lathe machines, you can just go download the post processor from our website and get running with that right away. Okay, so that's pretty much it for the printing, right?
Yeah, that's it. So then it was just a matter of putting all the pieces together, right?
Okay.
You sent me a bunch of parts,
Yeah.
or enough to build one full putter, right?
Yep.
I think it was, we were pushing on time on that.
Yeah.
And we put it together, put the shaft, put the grip on, put it together, took it to Chicago, and we did our presentation, right? The cool part was, we wanted to validate, did it work, right?
Yeah.
And we kind of validated it with looking at some of the simulation software. We used all this technology to put this thing together. But the key component to me was, okay, I mean, it actually shipped before I actually hit the first putt. It was in Chicago before I ever hit the first one.
Yeah.
And the funny part was, I was like, well, I wonder what the sound is going to be like. We plugged in that parameter, right?
Yeah.
And then we also said, what do we want to do at 10 feet? The cool part was we had some golf balls with us. We had a putting cup, and you're putting across carpeting, right? So it's going to play a little bit of plinko as it comes across there. And everybody that picked up the putter was starting to make putts.
Yeah.
And it sounded great.
It did sound great.
And it was like, all right, everything worked.
That was a little fortuitous because we were working in parallel a little bit, and that study didn't take into account all of the material properties that I brought to it with the printing. But we were pretty confident that the base parts that were probably going to carry the most mass and be most influential in the sound turned out to be true.
Yep.
That's cool.
Yep. It worked great. So now we're off to Gen 2 designs, right? Where we've changed this so we can get a more sturdy structure, right? And how do we get these parts to really go together, fit together better? And that's where we're at now. So.
Right, Gen 2, and then also making the manufacturing of the weights a little bit easier, right?
The powder's pouring out of it.
Oh yeah, we got powder coming out of it.
Yep. Cool.
All right, well, breathe slowly. That's fresh out of the printer this morning. So that's kind of a wrap on this project recap. I don't know about you, but I got a lot out of having this discussion.
Yeah.
More than just going through, making the content, and delivering that first in-person event. What do you think?
Absolutely. I mean, it's fun because sometimes you're at the live event and you're presenting, and maybe it's less personal or something.
Yeah.
But this one, was a little more personal. We kind of did a little more a deeper dive.
Yeah, and I think we gave the audience a little bit of a peek more on the behind the scenes of what's happening. So I think we should do more of these. This project recap session is something I'd like to do more of. If you guys are watching this, let us know what you think.
Yeah.
We covered a lot of different tools today. We covered SOLIDWORKS simulation. We covered 3D Experience Platform, PLM. Covered topology optimization, which was cool. I learned more about resonant frequencies in SOLIDWORKS. We covered the whole arsenal of 3D printing briefly: FDM, PolyJet, Xact metal, laser powder bed fusion, and Origin. And we just kind of touched the surface on all of that. So if anything caught your eye on this, head to our website and you can find more information, and also our YouTube page where we have tons of video content like this and more things like this about basically everything we work with. So, hey, thank you for spending the time to explain your expertise to me and giving me a chance to participate in this with you.
Thank you as well. Always great.
Yeah.
Good to see you.
You too.